So, have you ever really stopped to wonder how scientists know if a new drug actually works? Or, how a business can be 100% sure that one ad campaign did better than another? It's definitely not just a gut feeling. Today, we're going to pull back the curtain on the statistical power tools that let us find the real, meaningful differences out there in the world, t-tests and ANOVA.
All right, here's the game plan. We'll kick things off with the big question. Is there a difference? Then we'll get to know the t-test family, which is perfect for comparing two groups. After that, we'll see where that tool kind of hits a wall. And that's when we'll bring in the heavy hitter, ANOVA, for those trickier situations. And to wrap it all up, we'll give you a super simple guide for choosing the right test every time.
At the heart of so many questions in, everything, science, business, you name it, is this one simple idea. Are these things different? We might have data from a few different groups, but what we really need is a rock-solid way to know if the differences we're seeing are the real deal or if they're just, random chance. I mean, think about this classic scenario, right? You've got one group of patients who took a brand new drug and another group who took a sugar pill, a placebo. Their results look a little different, but is that difference big enough to matter? Is it statistically significant? This is exactly the kind of question these tools were made for.
Or, hey, what about this one? Let's say the average salary in the marketing department looks higher than in the sales department. But is that a genuine systemic difference? Or did we just happen to grab data from a few high-earning marketers by pure luck? See, we've got to move beyond just eyeballing the averages.
So, to answer these kinds of two-group questions, our first stop is one of the most popular hypothesis tests in all of statistics, the t-test. This is your go-to tool, your Swiss Army knife for making those direct comparisons.
And really, at its core, that's all a t-test is doing. It looks at the averages or means of the groups you're comparing, and it tells you whether the gap between them is big enough to be considered real and not just a random fluke.
But the t-test isn't just one single tool. It's more like a small family. As you can see here, there are three main flavors, and picking the right one is all about what your data looks like and the specific question you're asking. So, let's meet them.
First up, we've got the one-sample t-test. You pull this one out when you got a single group of data and you want to see if its average is different from some known number, like a national average or a target goal.
So for example, imagine we have data on how healthy, say, 50 managers in Austria feel. We could use a one-sample t-test to compare their average score against the known average health score for the entire Austrian population. It's just one group versus a known standard.
Next up is the independent samples t-test. Now, this is probably the one you're going to see the most out in the wild. It's for when you have two totally separate, unrelated groups, and you just want to compare their averages. Think an experimental group versus a control group.
And to answer our question from earlier about that salary gap, this is the test we'd use. We're comparing the average salary of one independent group, men, against the average salary of another independent group, women.
And finally, there's the paired samples t-test. The magic word here is paired. You use this when you have two sets of measurements, but they're coming from the exact same group of people or things. The classic example is a before and after scenario.
A perfect example would be measuring the blood pressure of a group of people before they quit smoking, and then measuring the blood pressure of those very same people 6 months after they quit. Since the measurements are linked to the same individuals, they're not independent, they're paired.
So the t-test is absolutely fantastic, as long as you have one or two groups. But what happens when our research gets a little bit more ambitious? Well, this is where we hit the ceiling of what a t-test can do for us.
Yeah, what if you're not just testing one new drug against a placebo? What if you're testing drug A, drug B, and drug C all against each other? All of a sudden, we have three groups. How in the world do we handle that?
Now, the logical first thought most people have is, oh, that's easy. I'll just run a whole bunch of t-tests. One between drug A and B, another between B and C, and then one more between A and C. Seems pretty straightforward, right?
Well, here's the catch. There's a huge problem with that approach. The critical thing to understand is this. Every single time you run a statistical test, there's a small chance you'll get a false positive, basically an error. With the standard cutoff, that's about a 1 in 20 chance. If you run 3 tests or 10 tests, those chances of being wrong just by luck start to stack up really fast, and suddenly your results just aren't trustworthy anymore.
So, to get around this problem of multiplying our errors, we need a new tool. We need something that's built from the ground up to handle 3 or 4 or even more groups all at the same time. And that tool is called ANOVA.
ANOVA stands for Analysis of Variance, and it's really a totally different way of thinking. Instead of doing a bunch of tiny comparisons, ANOVA is what's called an omnibus test. It's one single check that asks one big question. Looking at all these groups together, is there any significant difference to be found among their averages?
And just like the t-test, ANOVA is also a whole family of tests. You can see the different types here, like one-way or two-way ANOVA, which just depends on how many things you're testing. And there's also a version for related samples called repeated measures ANOVA, which is basically the big brother to the paired t-test.
So how does this thing actually work? Well, this slide gets right to the heart of it. The whole idea is to compare the signal to the noise. If your groups are truly different from each other, then the variation between the group averages, that's your signal, is going to be way bigger than the random variation within each group, that's the noise. ANOVA calculates a ratio of the two, and if that ratio is big enough, it shouts, "Hey, we found a real difference here."
Okay, so we've met the whole t-test family, and we've been introduced to the powerhouse that is ANOVA. The big question now is, how on earth do you know which one to use and when? Let's break it down into a really simple guide.
This chart right here is your cheat sheet. The very first question you ask is, how many groups am I comparing? If the answer is exactly 2, you're in t-test land. If it's 3 or more, you need ANOVA. Simple. Then, just ask if your measurements are related, like a before and after test on the same people. If they are, you use a paired t-test or a repeated measures ANOVA. If the groups are totally separate, you use an independent t-test or a one-way ANOVA. That's really all there is to it.
You know, at the end of the day, these aren't just some abstract concepts from a statistics textbook. They're like special lenses that let us see the world more clearly to separate the important signals from all the random noise. And that really leaves you with a final thought. Now that you know how to choose the right tool for the job, what hidden differences in the world around you could you start to uncover?